Hello, greetings from the ExecuTorch enablement project, which runs in collaboration of MLTech Czech Republic and MLTech China. Today we would like to show you the results from our first milestone, which focused on deploying a small convolution neural network using the ExecuTorch inference engine and accelerated by the NXP's Neutron NPU. We will use the MSys, what is the simulator for the Neutron NPU, and the Idotemics RT700 platform. Just a short recap, the ExecuTorch is an end-to-end solution for enabling on-device inference capabilities across mobile and edge devices, including wearables, embedded devices, microcontrollers, and so on. Moreover, ExecuTorch is part of the PyTorch ecosystem, one of the most popular ML frameworks. During this demonstration, we'll show the model preparation phase, and after that deployment of the CNN on the MSys and on the Idotemics RT700 platform. But before the demonstration, let us step back for a while and present you a brief introduction about the enablement what we are building here. Here is the overview of the ExecuTorch flow. Everything starts with an ML model in PyTorch, referred as PyTorch program. This one is processed by the ExecuTorch, which converts the model in the so-called ExecuTorch program. It is a file, typically with a PT extension. Optionally, one builds a kernel library containing additional ML operators for runtime if necessary. Now let's have a look how the acceleration of the Neutron NPU is achieved in more details. The ML model is processed by the ExecuTorch ahead of time part, the AOT, which identifies part of the model suitable for acceleration on the Neutron NPU. These parts of the ML model are encoded into TF-Lite format and converted with the already existing Neutron converter. This way we get the payload for the Neutron NPU. This payload is essentially the microcode, the weights, which are stored as Neutron needs them, and of course the kernels, which are used in the microcode. This is then stored to the PTE as a special ExecuTorch operator, or better say, delegate call instruction, with the Neutron backend ID. This ID helps the runtime to associate the individual delegate calls with the particular backend registered in the ExecuTorch runtime. Now what's happening in the ExecuTorch runtime? The runtime is processing the instructions from the ExecuTorch program. It reaches the delegate call instruction and calls the associated backend. In our case, it will be the Neutron backend, and this payload is essentially an executable for the Neutron NPU. With the help of the driver and firmware, it's executed and the resulting tensors are returned back to the ExecuTorch. Of course, processing on Neutron NPU is much faster and efficient than on CPU, so the inference of the ML model is rapidly accelerated. Just to emphasize the use of the TF-Lite format as intermediate representation between the ExecuTorch and the Neutron. This allows us to reuse the already existing Neutron software stack, especially the Neutron converter for Neutron payload generation, and extend the coverage to all NXP platforms having the Neutron NPU. Now, I'm handing over to my colleagues and they will show you the ExecuTorch in action.
In this part, we will demonstrate conversion from a PyTorch module to a PTE program runnable on Neutron hardware. PTE program represents model executable by ExecuTorch runtime. We will use the AOT Neutron compile.py script available in the ExecuTorch repository. For the purpose of this demo, we will work with predefined CIFARnet model. Model conversion itself can be split into multiple stages. First, we export the initial PyTorch module into the program in A10 dialect. It is intermediate representation that contains functional A10 operators and flow control operators. This is graph visualization of CipherNet program in A10 dialect. we can see operators for convolution, max pooling, softmax, and others. Next, program in A10 dialect is quantized using the neutron quantizer class. Quantizer ensures that the quantization is done in line with the requirements of neutron converter that is used in later stages of the conversion. Quantized program is then exported to Edge dialect within the export to Edge function call. Program in Edge dialect is ready for partitioning and delegation. Neutron partitioner internally identifies operators executable on Neutron. Such operators are grouped, transformed into our internal representation, converted with Neutron converter, and bundled into ExecuTorch delegate calls. This whole process is hidden in toExecuTorch function call and produces ExecuTorch program. Let's take a look on graph visualization of ExecuTorch program delegated to Neutron. We can see that most of the operations from CIFARnet model are represented by a single ExecuTorch delegate call. Delegate call wraps binary representation of the Neutron microcode, kernels, and weights, and offload execution to Neutron during the inference. Non-delegated operations represent quantization and dequantization of the input and the output. Let's now run conversion script. As we can see from the logs, we are going through all of the stages described previously. As an output, PTE file with delegated CIFARnet program is now stored in working directory.
Let us now delegate the CIFARnet model to Neutron. Before using the real hardware, we will show the run on NC simulator. We start this part by cloning an ExecuTorch integration repo. This repo combines the ExecuTorch submodule with the NC's driver from the Neutron software submodule. We will need a virtual environment with Python 3.10. We also need to install the requirements for the demo. The flow is driven by the run.sh script. First, this script downloads the NC simulator and the RISC-V toolchain. Then it builds the Neutron test binary by combining the runtime from the ExecuTorch repo with the Neutron driver from the Neutron software repo. Afterwards, it creates two CIFARnet 10 models. One model is a reference, designated for running on CPU. The other model is produced by ahead of time compiler, which offloads most time-critical operations to Neutron. At the end, the two models are executed on 10 classification inputs. We can see that the delegation to Neutron was successful, as the classification results are the same for CPU and NPU. In this demo, we will run the CIFARnet example on RT700 microcontroller. We will use the Visual Studio Code with installed MCU Expresso plugin and installed RT700 SDK. We have already imported the example from the SDK. The example uses ARM GCC toolchain, which needs to be compiled from the command line. First, we ensure that the path to the toolchain is part of our environment. Then we run the compilation. The created ELF file needs to be flashed to the board using the Seger probe. After flashing, the code is executed. We can see the result in the serial monitor window. We are seeing the run of CIFARnet model accelerated on real RT700 hardware. The inference took 11 milliseconds. This is a very small example, so after delegating the computationally intensive layers to Neutron, the overhead of quantization and dequantization operations becomes dominant. Stay tuned for larger models being enabled.